Hi everyone, this is Kalia from Marcus Evans. Thank you so much for joining us today on this webinar on driving UAV innovation, enabling heavier payloads and extending coverage. This is brought to you in partnership with Amprius Technologies. Before we begin, I'd like to cover just a few housekeeping items. As you can see at the bottom of the screen are multiple application widgets. They're resizable and movable, so please move them around to get the most out of your desktop space. I'd also like to encourage you to submit any questions that you might have by using the Q&A widget, and we'll try to answer as many as possible throughout the broadcast. However, if a full answer is needed or we perhaps run out of time, we'll make sure to send you an email afterwards. I'd also like to draw your attention to the resource list that will contain some interesting brochures, and please bookmark any links that you might find useful. To answer any common technical issues, I advise you use the help widget, and a reminder to look out for an email in the next 2 hours with links to review today's session. At this point, I just want to draw your attention to this disclaimer that just says that the views expressed during this webinar today are of our panelists and don't represent their employers. At this point, I'm pleased to introduce you to our moderator and our host. We have with us Stefan, who is the Chief Technology Officer at Amprius Technologies. Very happy to have you on. I'm going to hand over to you, and take it away.
Hello everyone, and welcome to this webinar. Thank you for joining us for this discussion on UAV innovation, which we will focus on batteries for higher payloads and extended coverage. This is a timely topic because UAV capability is increasingly being defined not just by the airframe design or the software intelligence, but by the energy storage and power delivery available. In many cases, the real limiting factor is not what the aircraft is designed to do, but how long it can stay in the air, how much weight it can carry, and how safely and reliably it can perform the mission. Better battery systems can enable longer missions, heavier sensors, greater operational flexibility, and ultimately better economics. So today we want to look at this topic through 4 practical lenses: payload, endurance, safety, and deployability. Our goal is to move beyond basic claims and get into what's actually changing, what matters commercially, and what will happen over the next few years, what we predict that will happen over the next few years. So let's start with the panelists. First, I would like to introduce David Waters, Senior Director of Operations Excellence at Honeywell. He will be joining us in the next few minutes. He had to step out for about 10 minutes or so. And I will let the rest of the panel experts introduce themselves. Trent, please.
Thank you so much. My name is Trent Clausen. I'm the President and Chief Engineer here at Titan Batteries. We're a battery manufacturer located here in Pocatello, Idaho, just about 2 hours north of Salt Lake City. And we design and build custom battery packs for the most demanding UAV applications and defense programs in the country and actually throughout the world. Titan sits at the intersection of cell technology and platform performance. So our goal is to turn these amazing world-class cells into flight-ready battery systems that actually work in the field.
Pete, thank you, Trent. Pete.
Hi guys, Pete Batar. I'm the CEO of Electric Jet Aircraft and also the co-founder of Leo Flight Corporation. We build jet drones that use electric jet propulsion as well as flying vehicles for human flight, including the Leo Jet Bike, which is a flying motorcycle effectively, and we're developing the Leo Coupe, which is a flying car for 2 people to fly around in.
Thank you. So before going to the panel questions, I will introduce the topics a little bit, and before that, I will say a few words about Amprius. In 2008, with a mission to develop the highest energy density batteries in the world by replacing graphite anode with silicon And after a good number of years of research and development, we indeed are delivering today this very high energy and high power with silicon anode technology. In the last few years, we have been focusing on pushing the battery performance for applications where every gram of weight matters, including unmanned aviation, with emphasis on combining high specific energy with the kind of power, charging, safety, and operational performance needed for real-world development. So what are the UAV applications that we're looking at, and how this slide sets up one of the most important points in the whole conversations. The fact that there is no single UAV battery. The term UAV covers a large range of platforms, from toys to weapons and everything in between. And each application puts a very different demand on the power system. The application defines the battery requirements, and the battery defines the capability. As we work through this segment, you can see here delivery, inspection drone, mapping drone, and FPV racing. There are many differences between the batteries. FPV racing drones live and die by the raw power density of the battery. They pull extreme spike in discharge for just a few minutes. So high discharge rate is the priority over endurance. Inspection and mapping platforms shift the balance towards sustained moderate draw of power over 15 to 90 minutes, where energy density and steady delivery matter more than peak current. Vertical takeoff delivery flips the profile again with the backstop curve. Very high power on takeoff and landing, low power cruise, which rewards high energy density lithium-ion cells that can handle the burst and deliver range for cruising. So with higher energy density, as long as they can deliver the power, any watt-hour per kilogram added to the performance, to the specific energy density, will extend the cruising time and the cruising range. In the next slide, they are all summarized in this table, which is available in the materials after the webinar. The defense segments shown in the gray or in the dark green stretch the power and energy requirements even further. Loitering munition need a long, efficient flight followed by extreme terminal power surge and abrupt cliffhanger profile. The Group 1 and 2 drones prize the lightweight, long flatline endurance. Sometimes they can be paired with solar power for multi-day flight. The heavier Group 3 and 4 for cargo and eVTOL platform demand high capacity and high voltage lithium-ion systems to move serious weight, while the HAPS, the high altitude platforms, stratospheric platforms, are a category of their own with a very low power requirement over day-night cycle discharging. So takeaway is that power, energy, discharge rate, weight, and cycle life have to be balanced differently for every mission. A cell optimized for an FPV racer is the wrong cell for HAPS, and vice versa. That diversity is exactly why tunable high energy density platform is so valuable, and it lets us match the battery with specific duty cycle instead of forcing every application into a one-size-fits-all. Referring to Amprius batteries, we have developed silicon chemistry for many of the applications shown in the slides before, with different power to energy ratios. That's what matters for each application. And in this power versus energy density chart, what should be remarked is that in all cases, the improvement relative to conventional batteries is substantial. Typically, in the 1.5 to 2 times across most categories of UAVs. Now that we have seen the variety of UAVs and the requirements for batteries, let's start the discussion with something mission related. Because that's what the operators care about. So, panel question 1. Heavier payloads and longer endurance are often in direct conflict. How do you resolve that trade-off today, and what would it take to stop making it a trade-off at all? Steve, I think.
So for us at this point, a lot of this has to do with different flight systems doing different things in the sequence of flight. So, for example, we have like a large vertical takeoff and landing clustered electric jet platform that carries a single person as an ultralight aircraft. We are developing a system right now for it to fly around 15 minutes per charge with conventional batteries or semi-solid state, like, cylindrical cells that are running roughly 300 watt-hours per kilogram. So kind of going back to the chart where it showed the different, we're kind of on the better end of the conventional batteries, but still not anywhere near the full solid state performance for that particular platform right now in testing. And what we're finding is that, we're running at roughly 50% throttle for 15 minutes. That's roughly a 4C output. So our discharge rate is about 4C on average. But when you talk about maneuver, you're going to spike that to over 10C, sometimes 20C. And generally speaking, we're running between 20 and 25C batteries to make sure that we cover the entire spectrum of performance, because your power density, your power requirement, your discharge rate has to not only be an average, but it has to actually take into account your maximum peaks, right? So heavier payloads and longer endurance, they are in direct conflict, but even within that sense, there is direct conflict between discharge rate and average power over time. And so, you think you can maybe do something, you're flying for 15 minutes. Oh yeah, you can do it with a 4C power rating, but you really can't, because that doesn't let you take off and cruise transition. That doesn't let you maneuver transition, spikes and things like that being taken into account. So those are some of the challenges, I think, and the thing that would stop making it a trade-off, I think, would be just something that had very high power density in peak when you need it, and then have average power density for cruise and non-maneuver flight. And I think some of that could be accomplished, and there are some things being done, I think, with ultracapacitors, supercapacitors to handle peaks, and then use batteries for your basic long endurance draw. Those are some conventional approaches now. It'd be interesting to see that technology integrated into an actual battery pack, all in one. But with current technology, that's kind of where you're at.
Yeah, as long as you can deliver the power, which is an absolute number, anything increasing energy density extends the range. David, do you want to add anything to that?
Yeah, I think I would agree with that. And I would say the best approach is probably to manage it as opposed to, a very difficult trade-off to completely resolve. But I think a few things come to mind that are important about prioritizing the mission, clearly understanding, what matters most, dwell time, sensing capability or range, and then you can optimize the platform and the mission for that. I think other things coming to mind as well for that trade-off and managing it would be system efficiency. There's a lot more than just the battery. The design, it can even be propulsion efficiency, power management, all of that play into how effectively you can convert that energy into performance. And, another thing is the innovation and the advances in energy density and how that's moving the curve. With all of it, I think the trade-off is always going to be there. It's just best to manage it as opposed to attempting to resolve it.
Yes. Thank you. We should go to the next question. Why is energy density becoming such a critical differentiator for both commercial and defense UAV applications? I think who wants to start, Pete, let's say, or?
So for this, again, we kind of go back to commercial and defense applications that have different missions. So optimizing your design matters a lot. That's why you're seeing a lot of UAS developing winged technology, because if you can use a wing rather than a propeller to maintain your altitude, you have some efficiencies there. But I think energy density is kind of obvious that the more storage you can create in a battery, the better. But again, it kind of goes back to the previous discussion about power density. Power density matters a lot. Your C rating, your discharge rate, how fast can you dump that energy out when you need it. And I think especially defense UAV applications, you're in a position where you have to have immediate power if you need it and be able to dump that power quickly. So some of what you're dealing with is systems of batteries. So you have maybe a cruise battery versus a maneuver battery or something like that, where your energy density is taken up primarily with, let's say, a solid state cell that has a lot of endurance, a lot of capability, but maybe not a lot of C rating. And then you can use either a lithium polymer cell or some combination of lithium polymer with ultracapacitors, supercapacitors for peaks to manage all of that. And it then becomes something that our friends at Titan Batteries do, where they can build a custom pack around the mission requirement. And I think energy density allows you to create a baseline around which you can build a custom pack then that meets a variety of needs. So as long as your core is sort of high energy density, then you can do other things to manage your mission through power density modification and things like that around that core. So I think that's one of the big differentiators in my mind anyway that comes to play every day.
Yeah,
I can add to that. Oh, go ahead.
I wanted to say that for an energy dense cell, the same C rate actually deliver more power, more current. That's usually not immediately intuitive, but that's what, if you calculate the amps out of energy dense cell, they are higher compared to smaller cell, less than energy dense cell.
I will say too that something in the solid state that matters a lot is one of the things that if you do tax a battery to higher power densities or higher power draws, higher discharge demand, you stress the chemistry with conventional chemistry, whereas solid state is much less stress in that same circumstance. And that matters a lot. Running in a situation where you need emergency power, you don't want your polymer catching fire, So there's a lot to be said for solid state chemistry from a safety perspective when it's under high demand. And that can be in temperature as well as demand. So yeah, that's a big deal.
Trent, you wanted to say something?
Yeah, I was going to say in a conversation earlier, Pete, you were mentioning also, so maybe if you want to talk on this too, and I don't want to put you on the spot, but talking about how distance matters more than flight time in a lot of applications, right? I know earlier we were talking about that. I don't want to steal your thunder, so did you want to talk about that? I'm kind of putting you on the spot, or we're talking about.
Fair point.
Go ahead.
So not to toot our own horn, but our propulsion technology uses small electric jets. We can fly really fast. I was showing Trent earlier, in fact, if you don't mind.
Show and tell.
This is one of our drones, yeah. this is one of our drones. It doesn't use propellers. It uses little electric impellers and propulsion systems that are extremely fast. I mean, this thing cruises at about 120, 130 miles an hour. And what that means is that maybe we draw a lot more power doing that, but we cover a lot more distance for the same size drone that can carry a pretty substantial payload. I mean, this thing produces about 80 pounds of thrust. So we can fly around at a higher speed and cover more distance in the same amount of time. So endurance is not as important in certain mission cases as distances. And for this one, it uses it for counter-UAS applications where we can impact a Shaheed, slam into it, and then come home because our propulsion is encapsulated. But we have to cover a lot of distance from the base. Ability requirement is kind of a big deal.
Thank you.
And again, we're trading time for distance.
Thank you. Let's continue with a poll question for the audience. We will spend about 2 minutes on this question, which is, what is your primary driver for evaluating next generation battery technologies? Is it A, extending flight endurance, B, supporting heavier advanced payloads, or C, reducing overall system weight, or D, meeting NDA compliance requirements? So again, what is your primary driver for evaluating next generation battery technologies? Extending battery endurance, A, supporting heavier payloads, B, or C, reducing system weight, or D, meeting NDA compliance? So please vote. Thank you. Go to the next, which should show us that compliance is actually very important. Next generation is more important than even extended flight endurance. Surprising. Thank you. Going back to panel questions. Panel question 3. What challenges still need to be solved before next generation battery technologies can scale more broadly across UAV ecosystems? So what challenges? Trent, you're building batteries. Want to?
Yes. I'd love to talk about that. Yeah, maybe the first thing to set the stage a little bit is that a cell is a cell. So a lot of people, when they go to the store, they say, hey, don't forget the AA batteries. They're actually talking about cells. And so a cell, that's one thing, but a battery is bringing together the cell, the battery management system, the enclosure, the user interface, the firmware, everything together that's needed to take those cells, to give that energy to that craft. And then we're looking to do that in the maximum performance and efficiency as possible. So we're trying to add as little headroom or as little baggage, extra baggage to that cell, both in weight and performance. And that's where companies like Titan come in. So to do this, we really need amazing engineers, battery engineers. So not just cell engineers. We need those too, of course, but battery engineers who understand that whole system. So it's not just battery engineering, but the drone as well. Because it's such an integrated system, what the battery does, how it affects the center of gravity, how it affects its compass, magnetic compass, how it affects its power curve. If a craft like what Pete is working on, if the powertrain is very optimized already and you're introducing a cell that has a different voltage curve, that's going to affect the powertrain. So these kind of things is what's so critical that our engineering is applying that heavily. So every craft is unique, every mission is unique, and so it requires that deep level, a system level understanding before we even start designing a battery pack. That's the other challenge today as well, is no two craft are the same. There are no standardization, broadly speaking, at this time. And because the missions are so unique, then every battery is going to require that pretty significant engineering effort to go from that concept to those through design stages all the way to production. What's different these days is historically it was sort of a lot of prototyping for a lot of years. Titan's been doing this for over a decade now, so we have thousands of prototypes under our belt. However, these days we're actually starting to get, significant digit or, quite a few zeros in volume of orders, and that's just really exciting because now we can actually carry past prototype into production stages. And so that also brings up the topic of just how fast innovation needs to happen. What used to take 6 months to a year to develop, we have to do in weeks or months now. This is because the missions, for example, drone dominance or the Gauntlet program that the Department of War is putting on, these gauntlets are taking place weeks, months apart. It's a very compressed, rapid iteration timeline. And so we have to iterate very, very quickly. And so programs are evolving, the platform's evolving, the mission's evolving. And so that also is a challenge because what you used to be able to do is spend a lot of time engineering a battery that could last 6 months, a year, years. And now that platform may only last for a couple of months before it goes through another iteration change. And so that just puts a lot of effort and strain on the engineering requirement. But that's what we're here for, right? I mean, America can make amazing things and our allies can make amazing things. And so we're working very hard, at least at our company, and I'm sure other companies are as well, to take that engineering talent and capability and really increasing it. The other thing too is taking these timelines. So there's, as many of you know, you're going through like engineering, through design, through production, and each one of these stages have to go quickly now, and so, but without skipping anything. You don't want to skip to production, only find out later that you missed something somewhere. And then just the last thing I'd say is certification, testing, because the compressed timeline, it really does mean that if you want to have trust and confidence that this battery is going to perform, we do need to make that efficient and quick. And then maybe just talking about the NDA compliance, just to react just quickly to that. It's cell availability, production capacity, and engineering capacity. And the United States is catching up quickly. When I talk to my peers and those in this domestic supply chain industry, things are going really fast, and the zeros are being added quickly. I think all the demand signals that we're getting are really starting to come to reality, and that allows companies like Titan to put real investment behind those demand signals.
That's great to hear. Anyone else wants to? Thank you for the very comprehensive answer. I think it was very good. Anyone else wants to add to this question, or we'll go to the next one? Yeah, probably we go to the next one because time passes. Panel question 4. In what ways is broader defense electrification accelerating innovation in battery technology and portable power solutions? So what is the role of defense electrification?
I'll start off with this one. I think when the defense industry, gets involved, that helps out move the industry along in many different ways. And so, number one, just with the defense demand, it increases the need for higher energy density. And I mean, they're using UAV, soldier systems, robotics. That creates more of a pressure to deliver more capability. So the industry has to step up and meet that increased demand. Also, defense requires a very deep level of system integration. It's not just so much power alone, but it's how does that power integrate with things like thermal management, autonomy, how does that play into the overall mission system and making that more efficient and intelligent in and of itself. And also, when defense steps in, it definitely increases the need for reliability of the product itself, but also for the supply chain. Defense normally have long tails of volumes that are needed, and they also are required to meet certain environmental qualifications, be more rugged, compliant, etc. And that also puts more demand on the industry to accelerate that innovation, not just so much in the performance, but also in the manufacturability, the supply chain, and as well as the sourcing for all of those components and products.
Yeah, thank you. We heard from Trent previously that the drone dominance program significantly accelerates the development of batteries and technologies for this type of applications.
Absolutely.
So, yeah. Anyone else wants to add?
Maybe just briefly when we talk to our partners in the government, they really do recognize that to have a sustainable solution for defense, it needs to reach commercial applications as well. And because commercial applications are often smoother, a little more consistent. You think about power tool batteries, for example, just speaking on our side. If we were to make a power tool battery, we could sell those week after week, quarter after quarter, very reliably on a long time horizon. However, a battery for a defense application, that might have, like David's referring to, a big spike, inrush, you order it, it closes, and sometimes those can be unpredictable, or the timelines might be affected on government budget, or the U.S., in our case, budgets. And so it can be harder for a business, a private company, to manage that. And so the department, our friends at the defense and the government level, they recognize this, and they are making efforts to make cell standards so that both commercial and basically they want the defense spending to spur a commercial, and they recognize that and they want that to happen. And so thank you, anyone here listening, because that really makes a difference for a private entity like ours to have that continuity of business.
Thank you, Trent.
Yeah, I think Trent really kind of covered that well, but I would just add that the more commercial demand there is, the more reason that defense would invest in broader electrification, because a lot of the defense applications are higher dollar, lower volume, and ultimately consumer electrification of various things like power tools, for example. That is a demand signal that if there is a follow-on market for the initial defense application, there's a higher likelihood that the Defense Department will invest in it, or the Department of War now. But all I'd say, battery technology, portable power, those things oftentimes start in defense and space, NASA-related kinds of applications, and eventually make their way to the individual consumer.
Yes. Yeah. Thank you. So next, we have another polling question. Which operational challenge is most limiting your UAV missions today? A, insufficient flight endurance. B, payload weight constraints. C, battery reliability at altitude or temperature extremes. And D, supply chain NDA compliance concerns. So again, what are the challenges for operating most that are limiting the UAV missions today? Insufficient flight endurance, payload weight constraints, battery reliability at altitude or temperature, and supply chain or NDA compliance concerns. So please vote. Give it a few more seconds. A, B, C, D. Thank you. So again, the NDA compliance or supply chain concerns is winning or getting the dominant position. Payload weight and battery reliability also seems to be a concern. Surprisingly, flight endurance, not so much. So let's go to the next panel question, number 5. How are compliance and supply chain considerations, including NDA requirements, shaping technology adoption this season? And is the U.S. industrial base ready to meet that demand? So this, we should take time here to respond, because it seems like this is indeed a very important topic. So 5, Trent, maybe you have to, yeah.
I know, I feel like we're on Who Wants to Be a Millionaire contestants here. So NDA, I think, is clearly really important to this audience. And it really makes sense, right? Because obviously the SEC made that a requirement. NDA compliance is big. The drone dominance program is driving a lot of this. And NDA compliance is more than just a checkbox, although we'll talk about that, of course, here in a moment. But I think it's really also about proximity and speed. So customers that we work with, the biggest value to them is the innovation rate. I want to talk about NDA compliance here just briefly here in a moment. But what also comes with NDA compliance, maybe a better way to say that, is people are in the same time zone, the same culture. The engineers can be on site. Again, speaking that innovation rate. So if somebody needs, they're invited to compete, they need a battery this week, can you do this? And so NDA compliance speaks to that, right? Because if these companies are in the same, within a few state borders away, this is something that our U.S. manufacturers can actually deliver on. And then that proximity compresses those timelines so that those engineering stages, the design stages, the production stages, that NDA compliance brings that in. Obviously, the U.S. industrial capability, our production capacity in the United States and allies is going to take time. But it's going way faster than I honestly thought was possible. So specifically, we're talking about cells. So getting cells out of China and into other countries, including the U.S. That's happening as well. But also battery management systems are huge for NDA compliance. So these are, again, where China specifically has had been doing this for years, and so it's going to take some effort to catch up to that. The good news is those are available today. You can absolutely get NDA compliant battery management systems right now. That's the hardware is NDA compliant, and the software, the firmware is written in the U.S. and you need, of course, both those for that to function. And then you need, of course, the battery itself. Things like injection molding, switches in the front, LEDs, all that, and of course all the engineering we talked about already earlier. All that NDA compliance, being able to have that domestically collapses those rates. It's happening now. You can absolutely get there. The challenge now is getting those zeros added. So going from 10 units, 100 units, thousands, 10,000s, hundreds of thousands, that's going to take some time. I think for us, just speaking on what we're seeing, adding capacity like maybe 10,000 batteries a month, it takes about a month or two to bring something like that capacity up. And where drone dominance needs something like 500,000 batteries over the next 12 months or so, roughly, then it's going to take some partnership between all cell manufacturers, battery manufacturers, printed circuit board companies, all these to work together to make this possible. And but it's absolutely happening. And for NDA compliance, it also goes to traceability. So for us, for example, we're working really hard to finish our AS9100 certification. So we can provide to our customers full traceability from the cell, like from Amprius, of course, all the way through all the different components that take to deliver that battery. And they're looking for that confidence so that when they go to take their craft, which includes the battery and the cells, when they deliver that to their customer, they can provide that evidence, and that evidence is being requested all the time now. I joke, it used to be, I've been doing this for over a decade now. It's only been in the last year or two that anyone even asked where these batteries were even made. And now they definitely care. And so it's very good to have that traceability available to our partners. So, I mean, I'm happy to hear that NDA compliance is there because, again, I really believe that, we were clearly over-reliant on China, and being able to return to a domestic manufacturing is going to help both our country, but also our defense, and we can step up and make it happen.
Yeah, I like especially what you said about the power of localized supply chain, of proximity. That speeds up development significantly when you can do multiple experiment iterations per month instead of waiting for shipping times and deliveries. Thank you. Going to the next question. How should organizations evaluate emerging energy technologies when planning future UAV deployments and investments? So this is continuing on the topic. Localized supply chains will accelerate progress, and how do we evaluate these emerging energy technologies for UAVs?
Yes, I'll step in on this one. And I think that what I would suggest for these emerging technologies in energy is for the industry, companies, individuals to evaluate those the same way they've evaluated the prior impact on other technologies in the past. I mean, first we have to look at, okay, well, what is the mission impact going to be? Does it meaningfully improve range, endurance, or payload? So looking at what that impact will be to the mission. Secondly, how difficult is it to integrate that new technology into the current system? Is it easy? Is it very complex? Does it require a redesign? What sort of risk does that introduce into the current system that any organization might be developing? And then thirdly, I think as we went through COVID and we experienced a lot of the supply chain constraints and shortages that we're now at the tail end of, I think, can it perform whatever this new emerging technology may be, evaluating it, and can it perform at scale? Does the supply chain meet the requirements, the needs, and the volumes for the future needs? And I think if any technology pretty much checks all three of those boxes, I think it's absolutely something to potentially move forward with. But as we evaluate those 3 or 4 things, normally it comes up short somewhere, and then that creates risk, and then we need to make decisions on what the tolerance of risk is as we might implement that or decline and wait till it's a little bit more mature.
Yes, and I will add also that different types of UAVs, as we have seen earlier, may have different risk appetite. So some advanced energy technologies will go first in particular UAVs and then toward others. Anyone wants to add to this topic? No?
Yeah, I would say that emerging energy technologies is it's not just about batteries in that sense. So you're looking at the potential for example, a long endurance type of surveillance system meant for high altitude, and it's maybe covered in solar panels where it's a very small battery, but it uses solar panels for direct power, something like that. So energy systems depend a lot on the application that you want in the end. So you're seeing these hybrid drive systems using fueled power sources. In addition, you're seeing fuel cell technology that has certain applications for certain things. It is a little bit cost prohibitive, but again, as you sort of enhance the market and the demand for all of these things, you're going to see a broader variety of solutions that come out of innovation houses that allow us then to select a variety of application-driven power sources for whatever UAS application there is. So I think all of the demand signal stuff that is both being generated by the Department of War as well as by agricultural industries and other applications for UAS, you're looking at a lot more reason to invest in a variety of sources of power. And obviously batteries seem to be on the acceleration path that we could ultimately get past gasoline-driven engines for direct power. It also is not far from going past fuel cell at this point, especially in a cost basis. So the technologies are already maturing, and battery electric seems to be the direction that this is going. But again, it's fully dependent on the kind of demand signal that's being generated by the applications.
Thank you. We have another polling question here, the last one. How important is a resilient supply chain in your battery selection process? A, critical, it's a requirement. B, important, but not a deal breaker. C, somewhat relevant to our program. And D, not currently a factor. So again, somewhat related and taking into account how much NDA mattered, I assume it will be not very well balanced, but how important is resilient supply chain in your battery selection process? A is critical, B is important, C is, or D, not currently a factor. Give it a few more seconds. A, B, C, or D. Thank you. So yes, it's important. As we probably could have guessed from the previous one, it's critical even. But in some cases, it may not be a factor for some applications. Interesting. Thank you for everyone that participated. Next, panel question 7. Looking ahead, what innovations are you most excited about that will enable your UAV performance over the next 3 to 5 years? So here, I think everyone can contribute. Pete, I think you're enthusiastic about new technologies. So
yeah, absolutely. So some of the big innovations, I mean, our friends at Amprius are really kind of bleeding edge right now, pushing forward on battery technologies. I think the solid-state battery technology is really the future. What the base chemical is that is used, so I've seen some things coming out of laboratories like fluoride ion batteries instead of lithium. Those kinds of technologies with different chemistry is interesting, and those energy densities are very promising, but there are always sort of these, opportunities and opportunity costs involved. For single-use batteries, you're seeing like aluminum air batteries coming to the fore where they're single-use and they can be thrown away in a one-way UAS. That seems to make a lot of sense in terms of both cost and energy density. But, again, there's a lot of experimentation that needs to happen. And it is exciting, though, to see, and it'll be interesting because there are so many different approaches to this problem and to the variety of applications that are sort of implied in this problem, that I think it'll be interesting to see sort of where everything falls ultimately. Having one battery that sort of does everything would be great, but I don't know that that's really the direction it's going, but it's exciting to see the different approaches to the different applications you can use batteries for that will enhance UAV performance. Especially, I think really the next 3 to 5 years are very interesting because you're also seeing this big energy demand drive from AI, data centers and the like. So, small modular nuclear reactors, things like that don't necessarily require fossil fuel to power our grid. And so as we are moving away from fossil fuel driven electricity, ultimately I think that is driven a lot by innovation, and the ability for us to switch to a battery based system is I think really even more in sight than it was a few years ago.
Thank you. Yes, there are many emerging technologies, and I think this UAV Cambrian explosion in a way of models will also produce significant development in technologies that are available. A variety of technologies that will be available. Batteries are used now more and more in pretty much everything. So I think we'll see some separation of sodium ion is good for something, lithium ion for something else, lithium metal for something else, solid state, and so on. Anyone else wants to comment?
Just mention that I would be remiss if I didn't mention that innovation that we need at the Department of War level is standardization. So the cells are working through a standardization process, but for the Department of War to be lethal, we can't have 20 different battery designs, 20 different chargers, 20 different LEDs, 20 different standards, it's too much. It becomes an operations administration's nightmare when you're actually in the field. And so we as an industry, speaking of the drone, especially the drone battery industry, are going to have to work closely with our cell partners and our drone partners to push standardization so that we have commonality between connectors, latching mechanisms, communications standards. So, for example, like many of you mentioned, Pete, earlier too, is you're going to want to put a certain amount of engineering into a single-use attack drone differently than you want to put into an ISR drone, differently into a reusable interceptor drone. And so, if you have all these standards, if you what we don't want the government to do is to say, well, let's choose every standard to make every battery have to meet every standard, because then that crushes innovation. And now every battery has to check every box, as it were. And so, but the good news is I really feel like the Department of War specifically and other organizations at the government level recognize this. And so standardization, I suppose, before I talk too long. Yeah, I think that innovation is going to be will be very valuable to them.
Yes. Typically, an industry will optimize our innovation for performance, and standardization will optimize for cost and for operational performance.
Sure.
Okay. Thank you. I think this was the last question I had. So we're opening now for audience questions. Please send your questions in. One question, how does silicon anode technology shift the competitive advantage for operators who adopt it early? Trent, you're working directly with silicon batteries. Cannot say from who, but
I know someone, yeah.
Please explain, have you seen a difference between when the start of use for silicon batteries versus before silicon?
Of course. I mean, what's always interesting, and anyone who's been in this industry for a while will remember, and certainly, as Pete called out earlier, a discharge density. In other words, how fast those electrons, if you will, can leave the battery is critically important. But A&L, as you mentioned it as well, if you double your capacity, you can have half the C rate and have the same amp output.
Yes.
And so when you're increasing from 200 watt-hours per kilogram to 300 to 350 to 400, you start hitting these top numbers. And what's interesting is you can start being a little more forgiving on the C rate, and then you get both. Now you get this high energy density battery at a C rate or an amp output that meets your requirements. Now you sort of get the best of both worlds. And so it's really exciting to see these high energy cells, like, for example, not to get too nerdy, but the SA08 at Amprius is very popular, let's say. Our battery technicians know that cell very well. And so this kind of technology, what that means is our customers can start saying, okay, I want to be able to do a mission that looks like this or a mission like this. Rather than having a battery designed just for one craft, just for one mission, just for one really narrow set, these higher density cells allow us to have a broader spectrum because we have the amp output as well as the density. But they can also start trading payloads, and that's really exciting too. So as we all know, but just to maybe state the obvious, if you increase your energy density by 20%, that either means you either can fly further, 20%, or you can add 20% more payload. And that trade-off is, of course, up to the customer. But often payloads are being able to have more capable payloads. I mean, that's excellent. Maybe one more thing to say on this too is if there's a nuance that maybe many may not recognize, if you're flying to your objective and that takes, let's say, a few minutes to get there, and you're there for, let's say, 10 minutes and takes a few minutes to fly back. If you were to increase your flight time by 20%, for example, you may actually double your on-position, on-target flight time. Because the fixed cost, if you will, of going out and coming back, that's already spoken for. But now you can be in position twice as long, or in a combat scenario, your contact distance can increase 2 2x. So if you're not, if you can reach out further, then you are further away from the lines. You are safer. And I mean, this is critically important to our troops and our allies.
Yes, thank you. That was very detailed. Another question, maybe for the operators here. What is the biggest limiting factor when it comes to broader adoption of next-gen technologies? Technical, commercial, or regulatory? What have you seen? David or Steve?
David, do you have any thoughts on that?
Which question was it again? I'm looking in the chat.
What is the biggest limiting factor when it comes to broader adoption of next generation cells? Technical, commercial, or regulatory?
I think I would say all of those three factors play into it: technical, commercial, and regulatory. It really depends on the customer's needs and what's being pushed that determines which one of those weighs the most. But absolutely, those three factors definitely play a part, and they're all kind of equally. I think in this industry, as things become more regulated, I associate that with standardization. Sometimes those two things can be a little bit different, but I think there being more regulations will open the door for more standardization, and that will also help reduce costs and create more affordability, which defense and commercial are always looking for. But I think that depending upon the specific situation, that will determine, what weighs most. But absolutely, it's going to be all three of those things that end up determining the momentum of the industry.
Pete, in your experience working with new technologies, which was the hardest to get? They didn't meet the technical specifications, or were hard to get, commercial, or hard to certify?
Yeah. I think certification is the least of our worries in what we do anyway, and it's not everybody's story, but I would say primarily technical, honestly. Technical and a little bit of supply chain availability and price, obviously, but technical is a big deal if we can get something that actually works and actually meets the specifications they actually advertise. So you see the advertised performance specs, and then you actually get it and you do experimentation with it, and you realize, it's not quite that good. So the technical challenges have been the biggest hurdles for us to this point.
Okay. So how, if it would be, to say a wish here, what kind of batteries would you prefer to have in the future? What is the aspect? How energy density changes the type of missions? What can you do with better batteries?
Everything really, like from our manned flight stuff, especially when it comes to like the jet bike, getting more flight time per charge is a really big deal for the consumer. Because we're also with the Leo jet bike, for example, we're limited by the fact that it has to remain an ultralight vehicle, which has a hard cap at 254 pounds. And so the 254 pound weight limit really does. Now we can tweak that a little bit and add flotation that can add like 30 pounds per float or whatever, and people have done that to fudge. But realistically, we're still trying to keep the weight as low as possible on the aircraft and still get more and more flight capability out of it. And that's the beauty of electric, is that when you have a vehicle, it's, if you have a gasoline powered vehicle or a fuel powered vehicle of any kind, it is where it will always be in terms of efficiency, because the fuel is never going to be that much more efficient than it is now. Whereas a battery-driven aircraft in 10 years could have twice the flight distance and flight time than with the batteries it had when it started. So those factors are really important, and especially when weight is capped at a certain limit. You're limited in terms of what you can do with your propulsion. Electric motors are already between 90 and 95% efficient, so you're not going to get much more out of electrical motor technology, to be honest. Some of that research and development has gone into how do you get more thrust out of the same motor stack, and that's possible that you might see a little bit of improvement there, but it's in the single-digit percentage range. You're not going to see doubling of your efficiencies in terms of your powertrain when it's electric. Whereas battery technology is really where everything is going to focus on increasing performance, increasing endurance, and still maintaining a certain weight limit so that you can maintain compliance with certain regulations.
Thank you. Yeah, we're out of time, so thank you everyone for attending this. I'll hand it back to Kyle. If we can have any other saying here. Thank you.
Sure. I just want to say a very special thank you to our amazing panelists for your great insights and being so generous with your time today. It was a very interesting discussion. On behalf of myself and Marcus Evans, we'd just like to thank you so much for the collaboration throughout. To turn things to the audience, we'd just like to say thank you for all the great questions and comments that came in. We weren't able to get to all of them. We'll make sure to reach out to you afterwards by email. A reminder to look out for an email within the next 2 hours with links to review today's material. And finally, we'd love to hear your feedback about what you thought about the webinar today. A survey will pop up on your screen in just a moment. We'd really appreciate any comments that you might have. On behalf of Amprius Technologies and Marcus Evans, we'd just like to thank you once again for joining us and hope to see you again at future events. Thank you, everyone, and have a fantastic day further.
Thank you.
Thank you.